Hi everybody, here's the start of our section 7.3 notes for logarithmic functions as inverses. Learning targets and what we're shooting for here are: I can write and evaluate logarithmic expressions, and I can graph logarithmic functions. Big ideas here are: the exponential function y equals b to the x power is 1-to-1. So its inverse, x equals b to the y power, is also a function. To express y as a function of x for the inverse, we're going to write y equals log base b of x. And that's how we say that, log base b of x. An exponential function is a function with the general form y equals a times b to the x power, as long as a is not 0 and b is greater than 0. b also can't be 1. In an exponential function, the base b is a constant. The exponent x is the independent variable, and the domain is a set of all real numbers. And we talked about that last section as well. Logarithms are exponents. In fact, log base b of a equals c if and only if b raised to the c power equals a. So, if these two numbers are the same, then c is your exponent on b. Take note, logarithm on page 451. A logarithm base b of a positive number x satisfies the following definition. For b greater than 0 and not equal to 1, log base b of x equals y if and only if b of y equals x. So keep in mind here that log base b x and y. Okay, this relationship is always true. So those numbers go in those spots. I like to remember that the b here is lower, and our b here is lower in that it has an exponent that's higher. And what it equals is the exponent, because remember, logarithms are just exponents. It's the way that we can write the inverse of our exponential function. The logarithm y is an exponent to which b must be raised to get x. So log base b of y equals x has a domain of x is greater than 0, and that's because our b to the x power equals y, our exponential, has a range that's y greater than 0. Remember, we have that asymptote, we never cross it, it's always positive. So our domain here has to be x greater than 0 because it's the inverse function. The range of our function becomes the domain of its inverse. And again, remember that log base b of y equals x and b to the x power equals y are inverses. So we have b raised to the log base b of a equals a, and log base b of b raised to the a power equals a. Because remember, we said that the two b's up here, okay, have to be the same. So since these are inverses, if we plug one in to the other, we get our x value. Same thing here. If we plug b to the a power in for x, we get a, get that x value. Example 1 here, exponential equation in logarithmic form. What is the logarithmic form for each equation? First of all, we need to figure out what our pieces are. So right now we have y equals b to the x power. Y equals 100. We have b equals 10. And we have x equals 2. Okay, our logarithmic form is log base b of y equals x. And remember I said that I try and remember that our b is lower than something, right? It has this exponent here. And our b is lowered here as well. So that's kind of how I remember, and then remember that the whole logarithm itself, so what the logarithm is just an exponent. So it equals x. Now that we know our values though, x, y, b, and x, we can plug those in. So we have log base b, which we said is 10, of y, which we said is 100, equals x, which we said was 2. Log base 10 of 100 equals 2. Same idea for part B here. Figure out what your x, y, and b are. So y equals b raised to the x power. So we have y equals 81, b equals 3, x equals 4. Y equals 81, b equals 3, x equals 4. We're going to use this formula again. So log base b of y equals x. Log base 3 of 81 equals 4. Okay, I'm gonna go through these here in a second, but go ahead and pause and try them. Okay, y equals b to the x power. So y is 36, b is 6, x is 2. We have log for logarithm base b, which is 6, of y equals x. And again, that formula is log base b of y equals x. Try the second one if you haven't already. Go ahead and pause. Okay, y equals b raised to the x power. That's our exponential form. Now if we use our formula here, log base b is our 2/3, and it's okay that it's a fraction for now. Log base b of y, or 8/27, equals x, and x here is 3. Perfect. When it comes to evaluating a logarithm, okay, we have log base 8 of 32, and we want to know what it is. So we're trying to figure out what it equals, and we know it equals x. In order to figure this out, just like with radicals, how we had to go, if we had different indexes, in radical form we had to go to exponential form, and if we had exponential form with different variables, we had to go to radical form sometimes. Same idea here. We're going to switch it to exponential form. And in order to do that, remember our base and our y. So right now we have 32 is y equals b to the x power. Y equals b to the x power. b, y, x. b, y equals x. Now that we have it in exponential form, we're going to try and get them so they have the same bases. So 32 is 4 times 8. 4 is 2 times 2. 8 is 4 times 2, which is 2 times 2. So we have 2 to the 1, 2, 3, 4, 5 fifth power. 2 to the 5th power equals 8 is 4 times 2, which is 2 times 2. Okay, which gives me 2 to the 3rd power. But I still have this x here, so to the 3x power. Okay, when I'm taking power to a power, I multiply my exponents. So because I have 1, 2, 3, it's 2 to the 3rd power, and then I bring down the x. Now that I have the exact same base, I can set my exponents equal to each other, because the only way that a number raised to an exponent equals the same number raised to an exponent is that the exponents are the same. That's the only possible way we can get to the same spot, as long as our bases here are the same. And our bases are a 2 and a 2. So we can take our exponents. 5 equals 3 to the x power. Because again, as long as our bases are the same, our exponents have to be the same in order for them to be equal. Divide by 3, and x equals 5/3, which means 5/3 is what log base 8 of 32 equals. Because that's what we said x was. Go ahead and try A here. Okay, I'm going to set it equal to x and switch it to exponential form. Y equals b raised to the x power. I have b, y equals x. So 125 equals b to the x power. 125 is 25 times 5, and 5 times 5. And remember, we're trying to get these both to be the same basis. So on my left-hand side, I have 5 to the 1, 2, 3 power, 5 cubed equals 5 to the x power. And the only possible way that these can be equivalent is if 5 cubed equals 5 to the x power. Our bases are both 5s, so our exponents have to be the same. So we can set them equal to each other. 3 equals x. And there's no other things that I need to do here to solve. I already know that x equals 3. So that's going to be what log base 5 of 125 is. It's going to equal 3. Try B, please. Go ahead and pause. Okay. Again, I'm going to set it equal to x. B, y, x. Log base b of y equals x. And y equals b to the x power. So 32 equals 4 to the x power, because we know b is 4, y is 32. 32, we've already said when we did our factor tree, gives us 2 to the 5th power. Again, if you're not sure on that, we take 32, 4 times 8, 2 times 2, 4 times 2, and 2 times 2. We have to break it down all the way to its prime factors, and we get 2 to the 5th power. 4 is not the same base as 2, so we need to break 4 down. 4 is 2 times 2. Our bases have got to be the same. We get 2 squared. And then we take that 2 times x, power to a power. Okay, the only way that these two can be equivalent is if our exponents are the same. So we take our exponents, the 5 and the 2x, and set them equal to each other because we have the same bases. So 5 equals 2x. To solve for x, we divide by 2, and we get x equals 5/2. So I'm going to put this over here because I'm running out of room. Log base 4 of 32 equals 5/2, because we said that is what our x is. I'm going to go ahead and stop this video here and start the next one.